you doing, Sam? So the power of these reactions lies in the fact that you can form carbon-carbon single bonds rapidly, right? The thing about this, as compared to the frustrated Lewis pairs, is that most of these processes are metal catalyzed, right? So with this is the probably one of the more popular organometallic coupling reactions. It's called a Stilly coupling, and it is a palladium. And what you'll see with these coupling reactions is you're going to see an oxidative addition step where your substrate adds to the metal. You're also going to see a transmetallation step where the metal uh, swaps partners with another metal, and then you're going to see a reductive elimination step. So for this particular reaction right here, the Stilly coupling, you have an organo 10 species that can be vinyl, aryl, or acyl. And then you have a palladium catalyst, right? And in this case, you can see the palladium catalyst here. It's palladium coordinated with acetonitrile and chlorine, and then the reaction is done in DMF and THF at room temperature with diisopropyl ethylamine as a base. All right. So here's the outcome. So you have these vinyl halides here. You have a vinyl uh, stannane, and this piece right here between the two tens, right, that vinyl group is going to couple between these two groups right here. So this will be like a ring closing strategy in an overall synthesis. But the vinyl 10 species is what facilitates that, right? So all of your coupling reactions are going to have like a similar mechanism, right? So you have first, here's your vinyl iodide. I just kind of abbreviated this. And this PowerPoint will be on Blackboard, so you don't have to scramble to try to write all this down. Uh, so here's my vinyl iodide, right? And that is going to oxidatively add to palladium, which is right here. Oxidative addition happens when a metal uh, inserts into a bond, a sigma bond, and the oxidation number of the metal increases, right? So here, this is the oxidative addition product, right? You have palladium with a covalent bond to a vinyl group here, and then iodine on this side. And then, and this is a generic mechanism that we can apply to, we can go back and look at the actual substrate, but this is how it happens, right? So if we went back, the palladium will oxidatively add here as well as here, right, on both sides. Uh, and then you would do a transmetallation step here to where whatever is on your 10 species ends up on palladium. So that's here, right? And that's why you need the something like this, right, where you would have vinyl distannate, right? Because you need that 10 to transmetallate with both palladiums. So you don't need two of these, you only need one, right? Because each one, after oxidative addition, each one of these is going to be, each one of these vinyl groups is going to be bound to palladium. So you need a distannate in order to do transmetallation on both sides, right? So whatever is on your 10 group here is going to get transferred to palladium, right? So that happens in the case of this molecule, that's going to happen twice, right? And then your palladium is going to do reductive elimination. That's the reverse of oxidative addition, where you form a covalent bond between this carbon and this carbon, and at the same time, you're going to decrease the charge on palladium by 2. Here you increase it by 2 when you do oxidative addition. But the actual uh, palladium catalyst is regenerated. So this is catalytic cycle, right? That palladium catalyst is not going to get used up. And every time it goes through this cycle, that's called a turnover, right? So every time that palladium catalyst goes through the cycle, that is called one turnover, right? Some catalysts can give you 1,000 turnovers, some can give you 10,000 turnovers. Uh, it just depends on the type of catalyst, but the catalyst itself doesn't get consumed. It just simply kind of wears out. All right. Any questions about that?
No, sir.
All right. So with the Stilly coupling, this is what you're looking for, right? You always look for 10, 10 and palladium, right? Those are your uh, reagents for Stilly coupling, right? The solvents can vary. Um, the diisopropyl, the base can vary, but you always want to identify tin and palladium. When you see those two metals together, then you know that it's a Stilly coupling. All right. Another very popular coupling reaction is the Suzuki coupling. Right. This is ubiquitous. This is used worldwide as a coupling reaction when you're trying to do a um, trying to form a new carbon-carbon bond. And a lot of these couplings are important again because you've seen already like these big giant macrocycles like FK506 or like prostaglandin, which is not a macrocycle, but it's a large molecule. But you can see immediately why this is useful. If you're doing a convergent synthesis where you have multiple fragments that you're trying to bring together, then these coupling reactions make those types of reactions possible, right? So you can see immediately why this is useful. And the other part of it is that the coupling reactions do not touch other functional groups. As long as you have your functional groups that are amenable to coupling, the other functional groups don't get touched, right? So with Suzuki coupling, you need an organoborane. Normally, it's like some type of boronic acid, and then your coupling partner is going to be a vital, aryl, or acyl uh, chloride, or it can be a bromide or a triflate, right? So here we have an iodide. So obviously we can include iodine in there, but you need a leaving group like a halogen or a triflate or something like that. And it's palladium catalyzed, and you need a base because the base prepares your boronic acid. Uh, so you can see right here, you got a lot of function. Go ahead. All right. I thought that was a question. All right. So you can see here, you have a lot of functionality. You got a lot of stereo centers present. Same here. And even with all of that functionality, it doesn't affect the reactivity of the coupling reaction, right? And you can see what happened. You couple basically this carbon right here where boron is with this vinyl carbon. So that's your final right here is your final uh, coupling product. All right. And again, very similar mechanism. This is generic, but it serves the purpose. So your palladium is going to insert or oxidatively add to your substrate. In this case, your palladium is going to add to here, where this to the vinyl iodide. So the vinyl group, the carbon in the vinyl group, and then the iodide are both going to be covalently bonded to palladium, whatever your leaving group is. So you have here, and again, you see you went from palladium 0 to palladium 2, right? And then with the base, whatever base you're using, in this case is cesium carbonate and DIA, but you do a ligand exchange here to get rid of the triflate. And what that does is it actually prepares the palladium to couple with the boronic acid, right? So here you take your boronic acid and you have to prepare it using a base like sodium hydroxide or something like that. But you prepare your boronic acid, and then that's where your transmetallation happens. Notice on the boronic acid, I have my coupling partner, right? This is what I'm trying to couple. So when the boronic acid interacts with palladium and you do this transmetallation step, you're actually swapping off this partner right here for the ligand that you exchanged for over here, right, which was a hydroxyl group. And then that transmetallation step gives you uh, this boride, right, negatively charged, and then palladium with both of your coupling partners on it. And after that, it's just a reductive elimination to form the carbon-carbon bond between these two carbons here and here and regenerate your palladium catalyst, right? So this is one of those reactions where uh, it's very facile, and it's also normally it gives you like really high yields, and again it's tolerant to a lot of different functional groups. So that's what makes it so useful as a synthetic tool, right? So Stilly coupling uses tin and palladium. The Suzuki coupling uses a boronic acid plus palladium and a base. The drawback for the Stilly coupling obviously would be the tin, because tin is toxic. So that's a little bit of a drawback, but it's still a very useful reaction. All right. And then you also have Negishi coupling, right? You can see here Negishi coupling works on alkynes, right? It's a great way to uh, to couple alkynes, right? So, and it's done in the presence of either nickel or palladium, uh, and you can have a vinyl aryl or alkynyl halides coupling with organo zinc species, and then palladium is a little bit better for this particular reaction. So you can see right here, if you start with an alkyne, right, you do hydrozirconation on that alkyne, and we've already seen that reaction, the hydrozirconation reaction, right, where you add this CP2 zirconium hydrochloride across the triple bond, and then you follow that up with zinc chloride, which does a transmetallation and swaps out zirconium for zinc. So this is my one of my coupling partners, and then I'm going to couple that with this, right? So it's going to follow a similar mechanism, and you can see right here why this is important. Number one, you can see the stereo centers are present, so it's tolerant to that, and it doesn't ephemeralize anything or doesn't change the stereochemistry of your substrate. Number two, the other part of its utility is that you maintain the stereochemistry of your alkenes, right? Your double bonds don't isomerize, then the stereochemistry doesn't change. You get what you get. So you can see right here, there's a new carbon-carbon bond being formed between this carbon that's bonded to zinc and this carbon that's bonded to iodine, right? And this is your product. And again, why this is so useful, because you can see these large complicated fragments, you can couple them together in one step very simply. um, and so Negishi coupling, obviously there's a transmetallation with zinc. You do oxidative addition, transmetallation, and then isomerization, so that the two coupling partners are cis and not trans, right? Over here they're trans, and then over here is the metal isomerizes, and now they're cis. Have y'all talked about that in 513? With metal complexes being either cis or trans or um,
I don't think so. Not,
really?
not
Yeah.
that I'm.
Have y'all talked about metal complexes at all in inorganic?
I think that's what we're heading into, but we haven't gotten into it yet.
Oh wow. Okay. 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 So yeah, your metal complexes, uh, depending on the geometry, right? Because you can have a metal complex that's square planar. You can have a metal complex that's octahedral,
Yeah,
You're
trigonopyramidal.
right, Dr. Russell. Yeah.
yeah, we went over that in organic. They don't go much into it, but I know in polymer science and like in the C side on like physics of materials, they go more into stuff like that.
Okay. 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 So yeah, so that isomerization happens so that those two groups can couple because even though it's happening on a metal, right? The the orbital overlap necessary for to make that bond still has to happen, right? So that you can't overlap orbitals if those groups are trans to one another. In this particular case, right? So you want those two groups to be cis, and then you just do your reductive elimination, right? Regenerate the catalyst, and it can go back through the cycle for another turnover. Uh, Again, all of these coupling methods are valuable. I mean, you can't underestimate or overestimate the value of these things because when you're trying to close up like a large molecule, a large macrocycle, because again, all of this stuff, well, not all of it, but much of it is targeted towards some type of synthetic target, right? Some type of synthetic outcome, some molecule that you want to apply your stuff to. Every method that's developed is developed with some larger goal in mind, right? So you just can't overestimate it. It's vitally important. And these discoveries like were vital to moving like the the synthetic organic chemistry enterprise forward. So uh, one other coupling method is here the Sonica shear coupling, and this is important because it allows you to couple alkynes, right? Everything else we looked at has been like vinyl or aromatic systems, and here you could actually couple an alkyne and keep the alkyne intact, right? That's important because in the product you have an alkyne, and if you want to do uh, some other perturbation to it, if you want to hydrogenate it, if you want to halogenate it, if you want to do some other perturbation to it, you can, right? And that's important because sometimes you want that alkyne. Maybe you need a specific alkene, but you don't want to couple you don't want to have that start out with the alkene because of some other process that may affect it before you get to the step where you want to react it. So that's why this is important. So if you have a alkyne, you can couple it with again aromatic, vinyl, or heteroaryl, which is what this species on the left is. Heteroaryl just means that you have heteroatoms either bonded to the ring or in the ring. So like a pyridine type of species or something like that. Um, so you normally use palladium and copper and a base, right? And then you do this in benzene at room temperature for 20 hours, right? You probably well, hopefully you're not thinking this, but maybe you're thinking that the benzene itself is going to couple, but it can't. You have to have some type of polarized bond that the metal can insert into in order for that coupling to happen. So benzene is pretty inert as it relates to these coupling reactions. All right. So the base is going to pull off the proton on that alkyne, which has a pKa somewhere about 25, 24, 25, something like that. So it's if you have a strong enough base, then you can definitely deprotonate that. And depending on the substrate that you're reacting it with, sometimes it'll do like if you react it with a something that's not aromatic, something that's prone to substitution, the alkyne when it's the acetylide anion after you deprotonate it, you can use it as a nucleophile. Sometimes, depending on the substrate, it can be used as a base. But here, right, you deprotonate it to activate it to participate in this reaction. So again, you got palladium, you have copper iodide, and then a triple bond and a aromatic halide, right? So let's look at the mechanism, right? And this again, this is on a pyridine type species, so it's a heteroaryl species. So the first step, same as always, is oxidative addition, right? And then the copper actually ends up on your alkyne, right? You deprotonate the alkyne, and then that adds to the copper. And if you think about this in terms of from an organometallic standpoint, like when you're making like cuprates or Gilman reagents, that's how you do it. You deprotonate the ligand, the alkyne, and then you attach it to copper, which we actually saw some cuprate, uh, the cuprate chemistry right before we did the FK506 stuff. All right. Um, this is interesting too because if you remember when we're talking about cuprates, right, the triple bond, uh, a triple bond attached to copper, it is really slow at being transferred, right? It has a slow rate of transfer compared to the others because of the back bonding that happens on with that triple bond and copper. But in this particular case, it does the transmetallation with palladium with no problem, right? And then you isomerize, right, to get you to here. And then once it's isomerized, you can do that reductive elimination, regenerate the catalyst, and start over. Uh, but the base and the copper will kind of work in tandem here, so you can generate this. It's not really a Gilman reagent, but this copper satellite complex, and then that's what does your transmetallation. Right. So the Sonica shear coupling is important again because of how it's used to close up uh, macrocycles and things like that. I want to, after we're done with this, I want to show you a paper because it actually, the when I first learned about this reaction, I was a grad student and one of the guys in my lab, well, a couple of guys in my lab, they were working on this natural product and the final step, they couldn't finish it, right? The final step was to close up uh, a ring of a macrocycle. It was like beryllium, which I'm gonna show you, and close that macrocycle up, and then that will finish the synthesis. But they could never figure out how to close it up. And then finally, they did a Sonica shear coupling, and that was the final step to close that up. So I'm gonna show you that once we get done. Another coupling reaction here is that what's called a heck coupling. It's an older uh, reaction, but very useful for building up alpha beta unsaturated uh, esters, right? So you here very trans selective. Uh, you use palladium and a base. Look at the catalyst load, 0.005% catalyst, right? That's almost nothing. So palladium catalyst, triethylamine, and then you can do this in water at 100 degrees for anywhere between 5 hours and 24 hours, right? Uh, and this is the mechanism for the head coupling. So you do your oxidative addition. Here, you do olefin insertion uh, into palladium, right? So you make a palladium sigma complex. And the thing about this type of insertion, the palladium can be alpha or it can be beta, but in this case, it prefers the alpha position, right? And then uh, you do beta hydride elimination, and that gives you your product, right? This is the beta hydrogen right here, and beta hydride elimination is a well-known organometallic observation, right? If you have a metal adjacent to a carbon that has a proton on it, that the hydrogen on it, that beta hydride elimination is a readily accessible reaction that happens, right? So you do beta hydride elimination, followed by, I mean, and then after that you have this complex, but you release that, and then you have now uh, a palladium hydride, which does reductive elimination to give you HBr, and then you get back to your initial catalyst, and then you can do it all over again, right? So the head coupling is a little bit different from the other coupling reaction because there's no transmetallation step, right? It's only one metal, which is palladium. But this is one of the first widely used coupling reactions, and again, these are important. If you look at how rapidly you can build up uh, alpha beta unsaturated ester, right? Remember when we were talking about olefinations, we did like the Horner-Emmons reaction, which allows you to build up alpha beta unsaturated esters. We did um, the Clark Steel modification of that, which allows you to build up alpha beta unsaturated esters. But this is the heck coupling also gives you a tool to do that, right? And it's highly trans selective, so that's even better. Um, so let me pull up this synthesis right quick, and I want to show you the application part of this. Let's see, what year was this? It had to be 2000. Yeah. So here is the let me go ahead and I need to open this in a different window.